Anti-disciplinary, and I'm going to steal that. It's really good. Well, I'm going to start today with a provocation, maybe a reductive one, that computers are rocks. That is their fundamental magic, or maybe it's ours, that we can draw these elements from deep within the earth, silicon, tungsten, copper, and tin, and transform them using labor and capital and language and a lot of energy into tools for divination and discovery. By miniaturizing them onto wafer-thin chips, we have turned rocks into oracles. And it's amazing, isn't it, what rocks have become? How far they've traveled from the depths of deep geologic time to these accelerated calculations of contemporary computing. They've given us enough raw computational power to do previously unimaginable things, like model the climate and discover and synthesize unknown molecules, to send poetry spouting from chatbots. But there are limits to what rocks can do. For one, the cold, hard edge of physics is near. Miniaturization can only take us so far. The cost of fabricating next-generation computer chips grows more and more prohibitive the closer we get to the limits of how small they can be. But there's also only so many rocks left to do it with. Demand for the high-purity silica sand that's used to make silicon chips is currently causing a global and irreversible shortage of sand. And the supply chain for minerals commonly used in smartphones and batteries and in computers fuels bloody conflict and exploitation and untold political chaos around the world. So what comes next? After we've drawn blood from the final stone, we're going to have no choice but to transcend this paradigm, to transcend these smart rocks, which will take some adjustment because we're very used to them. But I think that in the future, rather than silicon, tungsten, or tin, the computers of the future will have to be mined from a lot stranger stuff. In fact, they may not be mined at all. They might be grown. And if that sounds weird to you, then you've never met a slime mold. Fortunately, that's easy enough to correct. Unlike silica sand, slime molds are abundant on this planet, and they tend to regenerate. Just go to your nearest forest, I'm sure there's plenty around here, and turn over a log and look into the loam and the damp and the rot at that edge between life and decay, and you will find them. And when you do, you will probably think that you're looking at a mushroom, a fungus of some kind. You wouldn't be the first to feel that way. Slime molds have been miscategorized, misunderstood throughout history. Their Latin name is mycetozoa. Myceto for mushroom, zoa for animal, so some kind of fungal animal, which is unusual. But they are not fungi, nor are they animals. They're something much, much stranger. Acellular organisms, as in having no cells at all. They have a truly unique physiology. The body of this slime mold, Physarum polycephalum, is a single amorphous cell, this unctuous yellow, electric yellow, enveloping slime that harbors thousands of loose nuclei which pulse through the organism in this rhythmic shuttle flow as it forages for resources in its environment. This allows it to travel through its environment at a remarkably quick speed for such a small organism, at about 1 millimeter per second. And as it travels, it sends out these searching tentacles called pseudopods as it forages for food. And where it doesn't find food, it retreats those tentacles, leaving behind a chemical trace called an extracellular slime that signals to the body not to return. Now, what's interesting is that trace and the mold's inborn capacity to reread it constitutes a form of spatial memory in an organism which does not have a mind, which does not have a central nervous system, no self-awareness, no knowledge that it's doing so. It can still explore and map its world in staggering detail. And that means that this humble, humble organism in the right context can solve mazes and design efficient networks, easily find the most efficient path between different points on a map. It makes quick work of the U-shaped trap test that's usually used to test autonomous robots and self-driving cars. It's modeled the roadways of ancient Rome, charted new paths across the moon and Mars, and traced a perfect copy of Japan's interconnected railroad networks. It's expert at the kind of network optimization problems that we call traveling salesman problems, which anybody in computer science knows are extremely difficult and extremely inefficient to solve using conventional computational means. It doesn't use conventional computational means. It uses unconventional computational means, something we call morphological computing. It thinks with form. It thinks with its body. And for certain problems, specifically those which are really inefficient to solve using traditional means, form is a really interesting way to think, a really useful way to think. And although it might seem counterintuitive to us, it is able to think with a body and without a brain. Now, what does that mean to think with a body and not a brain? I think one way to approach that question is to look at the inverse, thinking with a brain and no body. And I think that's a fair enough description of the aspirations of artificial intelligence, of deep learning, of the project of emulating the synaptic connections of the human brain through artificial neural networks to create AI systems. I mean, traditionally, AI emerges from these models of the brain because that's where intelligence is, right? Well, it certainly is where some intelligence is. But if we actually look at biology, we discover that intelligence is a lot more amorphous and weird than we think it is. For one, I mean, Physerum shows us that there are ways of thinking which transcend the brain entirely, which are purely embodied. So when we consider the brain in isolation as though it was a brain in a jar or in a vat, we're kind of ignoring that form of intelligence, which, although primitive, is highly useful in very specific circumstances. We're also ignoring that even in humans, the brain is situated in a body. And in that body, microorganisms outnumber human cells 10 to 1. What do those organisms know? How does their primitive intelligence guide our own? And what about our other cells, our non-neural cells throughout our body? Do they have a form of knowing? Can they remember? These are open questions in biology, but what we're beginning to learn is really startling. Because for decades, the prevailing wisdom in neuroscience and biology has been that memory and learning are consequences of synaptic plasticity, that the connections between clusters of neurons that are simultaneously active during an experience strengthen into networks that persist even after that experience has passed, right? That's commonly expressed by the adage that neurons that fire together wire together. It's fundamental to our understanding of memory and cognition in humans. It's also obviously undergirds the design of artificial neural networks. But more and more emergent biological research suggests that synaptic plasticity is just not the whole story when it comes to intelligence. It doesn't explain things like the slime mold's very unique way of mapping the world. It doesn't explain how far more humble cells, non-neural cells, both within and beyond the body, can also remember and learn. Now, memory takes many forms in the natural world, not all of which we feel comfortable calling memory because we have a very affective human association with that word. But if you look at bacteria, for example, all bacteria perform chemotaxis, which is the process of traveling along chemical and temperature gradients to more ideal environments, better conditions. Now, they wouldn't be able to do that without the capacity to compare their present experience with their past experience. Bacteria do this in a very primitive way. It's an aneural form of cognition, but like the slime mold's morphological computing, it does effectively result in something like memory. In the realm of the eukaryotes, unicellular creatures have remarkable capacities. This is the ciliate, Stentor roselli. It's a unicellular pond-dwelling creature. If you irritate Stentor roselli with a little pipette of microbeads of plastic or a little jet of dye, it will react like any living thing. The first thing it will do is turn away from the irritant. If that doesn't do it, then it will reverse the direction of its ciliates, essentially spitting water at its persecutor. If that doesn't work, then it will retract into its holdfast, which is its little station that binds it to its environment. And if that doesn't work, and once it's well and truly exasperated, it will detach from that holdfast and swim off to find more favorable conditions. Now, this looks like animal behavior, doesn't it? It's a hierarchy of reactions to an experience, each of which requires prior knowledge of something that came before. You can't ratchet up your response to an irritant if you don't know that the previous response didn't work, right? That also is memory. But this is another creature which has no neurons. It has nothing but a single cell. But yet it retains this awareness of past and present environmental conditions. And that awareness is something that's present in maybe all non-neural cells. A study just last year found that human kidney cells can remember too. And not only that, they exhibit what's considered to be a cornerstone of memory formation in humans, something called the mass spacing effect, which essentially means that, like us, they remember experiences for longer if they've been exposed to that information in spaced intervals rather than cramming it in all at once. So anyone who studied for a test all one night before the test and then forgotten everything a few days later knows about the mass spacing effect. It's universal. In people, it's also common across the animal kingdom. Bees show it, fruit flies, sea slugs, birds, monkeys. And now, perhaps, we are learning that it permeates actually down to the single cell, suggesting that these more basal forms of cognition exist, more basal than neuroscience has previously acknowledged. That means, by implication, that cognition is something that's everywhere. It's naturalized in life down to the smallest elements. We're just now uncovering this, and there's still so much that we don't know about how life knows. And even those things that we do know, we struggle to capture and represent through computational means. Take, for example, the microscopic roundworm, c.elegans. It's one of the most closely studied animals in all of biology. It's been a model organism in labs since the 1940s. We know so much about it. We have maps of every single cell in its body, of the 302 neurons that constitute its brain. We've mapped them with electron microscopes. We can use genetic imaging techniques to turn those neurons individually off and on and see how the rest of the brain responds. We have a complete wiring diagram of these 302 neurons that constitute its brain. 302 neurons compared to our 82 billion. That's about as simple as a brain can be. So you would think that artificial worm intelligence, I mean, we've been talking a lot about AGI and ASI, but AWI should be right around the corner, right? It should be crackable, but it's not. In fact, so far, the dynamic behavior of these 302 neurons is essentially incomputable. Simulating it, simulating a c.elegans brain is considered one of the thorniest and most intractable problems in computational biology. One researcher I spoke to for a piece I wrote about this told me that it was like a cathedral. Like he didn't imagine it would ever be built in his lifetime, although he was happy to participate in the project. It would take an enormous amount of data, good data, an enormous amount of compute, an enormous amount of researchers and collaboration, all to do something that a microscopic nematode can do with nothing. And I think that's so humbling, isn't it? I think it's important to underline how incapable sometimes, how inadequate our existing computational infrastructure is at expressing the very basic and most simple things in nature. That's not to say it's not worth doing these things. It is. Because worm AI can be a stepping stone to fruit fly AI and a stepping stone to rat AI, and maybe someday a really full and robust understanding of how the human brain works. We have to start somewhere. Lessons from the Physarum polycephalum slime mold, although a humble organism, teach us a lot about how to build resilient networks. Mathematicians have simulated Physarum's behavior to map the largest scale structures of the universe, the cosmic web. And on a practical, material level, there are researchers in the field of unconventional computing who are actually working to build hybrid biocomputer chips using Physarum's body by injecting those pseudopods with conductive nanoparticles to create really primitive and yet completely sustainable, biodegradable living computer chips. Now, these are speculative efforts, of course, maybe mostly thought experiments, but I think it really puts the whole smart rock thing into perspective. I think when we start looking around us at the natural world, we can actually find a lot of interesting solutions to our problems. We think our problems are unique and modern, but they're not. Only a few years ago, a researcher at Stanford, Dr. Deborah Gordon, ant scientist, found the regulating algorithm that harvester ants use to determine how they will forage for resources across the Arizona desert is functionally identical to TCP/IP, the transmission control protocol that we use to regulate data traffic across the internet. The internet, okay? I had to say it. But does that mean that ants are computer scientists? No, it just means that they've had millions of years to solve problems that we've only had for a few decades. Why aren't we looking for more of these problems and with more of these baked-in solutions? What other ideas can we borrow from nature? Because ants and slime molds and worms, they're really useful model organisms in a laboratory context, but they are not unique in the living world. As the computer scientist Selim Akil observes, computation is ubiquitous in the universe. To be is to compute. And he's not speaking metaphorically, and neither are the biologists who are increasingly using terms like algorithm or information processing or memory or compute to talk about what they see in the field. Because what is computing, if you really strip it down? It's the capacity to process input, in the case of a living organism, information about the environment, to encode that information in memory, to retain that information through time, and then to act on that information in order to change behavior and create new outputs. And then ideally, to feed that output back into the system and continually improve it, right? That's basic computing. It's also basic to the evolutionary survival of any living thing. What we think of as computing, like operations in silicon and tin, it's really a specialized instance of a much more ancient and broad process, a process that spans materials, substrates, and millennia, and phyla, and exists at many degrees and scales of complexity. Again, to be is to compute. Now, this is kind of the inverse of how we think about computation now, right? Because since the invention of big data processing machines in the mid-20th century, we've really bent over backwards to make our world legible to them, right? To compartmentalize all the complexity of nature, of life, of our world into this mathematical, logical world model. In that process, we've done a lot of amazing things. There's no denying it, but we've also kind of diminished life. We've diminished that messiness and that capacity for transformation and change that is inherent to life. Life is a dynamic process. It's not something that can be easily reduced. It's something that emerges from the interaction of constituent parts at multiple scales, right? It doesn't fit neatly into boxes. So if we built our technology from the earth up to model these more primitive processes, the way that nature processes information, we might not be jamming square pegs into round holes. We might have space for all that messiness and that aliveness and that transformation. We've heard so much today about AI tools and agents, all these fellow travelers with which we're going to share the coming decades. But we already have many fellow travelers all around us in this world and within us. And they teach us a lot. They also teach us the difference between representation and reality, by which I mean that AI systems are trained on data. They're trained on words, symbols, images, code, sounds. These are representations of the world. But intelligent living systems are always engaged in a dynamic, material, embodied relationship to reality. Physarum has no sensory organs with which it can represent the world to itself, right? A cell cannot represent the world to itself. It can still act. It can still negotiate with its environment physically, inviting its environment into this ongoing give and take that is chemical and tactile and physical, that's bound up in the consumption and excretion of matter, the transformation of matter through digestion and decay, these ancient processes, none of which operate in isolation, by the way, because life is a conversation. All intelligence on Earth, all complexity, all information processing, be it human, slime, worm, ant, it all emerged as the result of a very long and open-ended evolutionary dialogue, a process through which every living thing found its mind in time, in conversation with other minds and with its environment. Anecdotally, neurons first evolved around the time that animals started eating each other. So the fact that we have complex thought at all emerges from an evolutionary necessity to be aware of the proximity of other animals. And that doesn't mean that intelligence is rooted in hostility, by the way, because in so many cases, survival, evading predation is a question of collaboration and not necessarily competition. But evolution, time and time again, is the thing that has brought us the complexity, the cognition that we seek from our computing systems, right? So why not work towards intelligence from that direction, from the ground up rather than from the bottom top down? It's the only way that we know has worked. You know, the fact that I'm up here talking to you and you're all out here listening is evidence of that. Our understanding of the living world has always evolved alongside our technology itself. And for the first half of the 20th century, biology was dominated by this mechanistic, linear, reductionist view of the world. This idea that the structure of things determined their function. So cells were units, ants were automata in an inflexible hierarchy. Life was something to be dissected and examined and taxonomized and broken down into its parts and looked at under a microscope, taken apart like a machine until it could be understood. And that was a reflection of the computational paradigm of the time, as it always is. But computing is a metaphor, and it does evolve. It can evolve alongside our understanding of life. our understanding that life is a dynamic process that, again, is defined by interactions between constituent parts. That is not something that can be broken down. And I think as our computing power has grown, our capacity to understand that has changed. Our capacity to model and simulate living things has improved. And it's given birth to new ways of looking at the world. It's given birth to new fields like complexity science or artificial life. And computing as a metaphor has given biologists new language for talking about what living systems do. Language that brings us together, ours and theirs. Language that helps us understand how life processes information and preserves information in order to keep entropy at bay, which is life's fundamental magic. I would like to express to you my hope for the future, which is also kind of a call to the deep past. I really believe that we're getting closer and closer to bridging the gap between technology and life. Although the closer we examine that gap, the bigger it seems to get. I do believe that bridging it is within the realm of capacity. Perhaps it's the final cathedral that we'll have to build. And I hope that once we've built it, it can save us from ourselves in a sense. I don't just mean that someday I hope we'll have machines that are, like I said at the beginning of this talk, not mined, but grown. I hope that we can also use those machines for something, to understand more deeply the mechanisms of the living world, the patterns which underlie its creativity and its resourcefulness, its mutualistic networks, its remarkable capacity to adapt to circumstances, its relentless drive to survive, to persist, to thrive in the face of all odds. I hope we might find a way to understand the world using tools that are modeled after the world, tools that are generative, resilient, even alive, not static and unforgiving or as unyielding as stone. Because that's when we can finally become what we've always been meant to be, what we've always been, which is little more than a way for the world to know itself. Thank you.